Hello class, so this is just a quick video on electric fields and flux. So your objectives are to know the definitions and know how to solve problems regarding the field and flux. So the formal definition of electric field is a region around a charged particle or object within which a force would be exerted on other charged particles. So what that's saying is if, say, for example, we have a positive charge, it has an electric field, which we can show with our field lines. So there isn't a force because there's nothing else. It's in space alone. However, say we throw in a negative, let's make it a negative. Say a negative charge here. Those field lines would essentially intersect with our negative charged particles field lines, and then therefore they would both feel a force of attraction to each other. So an electric field just shows how much force there would be if we put a particle there, but it does not tell us the actual force until we add another charge. So electric flux is a measure of the flow of an electric field through a given area. So these definitions are highly related. So if we still have that positive charge giving off its positive field lines, we could then, say, put up some sort of surface to measure how much flow will go through that surface. This is called the flux. Flux is very important to generators and capacitors, how much electric field we can get through a given area. So the way you want to remember the definition for this inside a plane, we'll later talk about closed objects, but inside a plane is we therefore need to know how much electric field there is, how strong is it, the area, and if it's at an angle. Because say if it's at an angle, the amount of field lines that are going to be able to go through it are going to be much fewer. And we would denote this with cosine theta. So this is the electric field. The area of your surface. And it must be a surface, not a closed object. This is how much it is tilted. Alright, so now we're going to do a practice problem involving, remember to try it first, and then come back for the answer. Alright, so calculate the total given flux from a surface that is 2 meters high, 0.5 meters wide, with the electric field being at an angle of 25 degrees, and an electric field of strength 9 times 10 to the negative 7th Teslas. Now that you've had a chance to solve it, so remember we care about the total electric field strength, so we put in your electric field, multiply that times your area, which since this is a rectangle, that is length times height. And then you want to find the cosine of your angle, which is 25. And the answer would be 8.16, or if you wanted to round it, I would take 8 times 10 to the negative 7 power. Alright, so tomorrow we're going to start working on something called Gauss's law, which is also using flux. But this is saying exclusively for a closed surface. So until now we've been using flat surfaces, which are in no way closed. Think of more of like a box or a closed sphere. So it only works with a closed surface. So it is the electric flux is equal to the charge that's enclosed. So this is when there is a charge inside of a surface, divided by the permittivity, which is E, or epsilon, the Greek letter E. Alright. Epsilon is just like K, it's another number, which is, it's 8.85 times 10 to the negative 12th. So permittivity is just epsilon, which is, again, 8.8 times 10 to the negative 12 coulombs squared over newtons meters squared. This only works for a closed surface. This is a very important point. So if it's a flat plane or not closed, this is the formula you're going to use. However, if it is closed, such as a sphere, then this is the formula you're going to use. So there's two. So you have to think, is there an enclosed charge, or is it simply a flat surface? Alright, so we're going to do a practice problem with this one. Alright, so you have a point charge of 6 coulombs inside of a sphere with a radius of 10 meters. So what is the flux in the sphere? So go ahead, try it. Alright, so to solve it, it would be 6c over epsilon, which is 8.85 times 10 to the negative 12th, which would get you 6.8 times 10 to the 11th power. So when you're doing these, don't worry about the radius, because the radius really doesn't matter. The total flux will solely be determined by the enclosed charge and the permittivity constant. So remember, we defined the electric field as the force per a charge. So another way to write that formula, so remember that Fe is equal to K1 over Q1 over Q2 over R squared. So if I were to say plug all of this in for Fe, we would have K, Q1, Q2 over R squared, as well as over Q. So when this happens, we can see we have two Q's. We can cancel our Q's on bottom. So a way to simplify this formula, and one that will be very useful to you, is K times Q over R squared. So remember, K is still equal to 9 times 10 to the 9th. Q is just your charge for whatever is creating the field, and R is your radius. Alright, so we're going to do one practice problem and finish this video up. Alright, so try the problem. It's find the electric field 2 centimeters away from an electron that is, from an electron. All electrons are negative 1.6 times 10 to the negative 9th coulomb. Alright, now that you've had a chance to practice that, so first off, 2 centimeters is not going to work. It needs to be in meters. So remember, the way to turn this into centimeters is divide by 100, or move your decimal over 2 places, so it's 0.02 meters. Alright, then we want to think about our equation, which is that the absolute value of the electric field is equal to KQ over R squared. K is 9 times 10 to the 9th. RQ in this case is negative 1.6 times 10 to the negative 19th over r squared, which is 0.02 meters. Square that. This will give you negative 0.00004, or if you're writing in scientific notation, 4.0 times 10 to the negative 6. Alright, hopefully this wasn't too difficult for you. We will be talking more about this tomorrow and on Friday. Happy physicsing.